Hi, thank you very much. First of all, I don't pretend to be any expert on shaft voltages and currents. I'd say Steon's stuff is advanced. I was a bit concerned at the beginning of the talk that I suddenly thought I should have told Prof I should have spoken first because I'm introducing the topic. I offered to do this just basically for that reason, because there's a lot of aspects to shaft voltages and currents, and it's a field that goes between sort of electrical engineering, some mechanical, and you tend to find specialists in certain areas. So I've tried to summarize what I've learned over the years, and I also learned a few new things, and I've learned one or two things today. So I mean it to be quite informal. I haven't set a time, Prof. So if I go over time and people start falling asleep, just let me know. And I just wanted to show you something off the topic, but still related to rotating machines. We were lucky enough to have to rewind an ESCOM machine recently, and in it they called for a destructive test. So the coils were 11 kV globally VPI'd coils, and in order to test the process of the vacuum pressure impregnation, you make what they call a formet. It's 2 coils, sometimes more, and you put them in the VPI tank at the same time that you VPI the main stator. So then you take them out and you can test them, you can cut them open or whatever, because the only way you know how good a vacuum pressure impregnation process is by cutting open the coils, and you don't want to do that on the completed stator. Anyway, so the coils are rated at 6.35 kV to earth, it's phase voltage. And their test required, the coils take 46 kV RMS. Only for a couple of seconds, they just had to prove that they managed it. So we took the coils to that after blowing up our own internal high-pot supply, not blowing it up really, but just putting it out of action. And we took it across the road to LHM, to their transformer facility. And we took the coils to 46 kV, they stayed there, so then we said, okay, we'll take the thing to 60 kV. And after a few seconds, it should fail. So this is the 60 kV. It's more exciting with sound, but I mean, I didn't think of that at the time. Maybe I can. And you can see most of it is tracking on the ends. And it sat at this for 2 minutes, and it still didn't break down. So the ESCOM procedure calls for full destruction. So we then took it to that point, and that was 76 kV. And this was the 76 kV. And you'll see it breaks down over here. That's it. And it didn't break down in the slot portion. Anyway, I thought you'd like that because it's the most fun I've had in a long time in rotating machines. We still haven't stripped it or dismantled it.
What were the current ratings when you did that?
What were they?
The current levels.
You know what? I've got that on a WhatsApp. I'll show it to you later. All I can see is the scale because I was sitting doing the video and someone else was recording the currents. But you can see at the end where it does that, the current goes right off scale. It's a nice high-pot test set because it's got 2 series reactors, so it can really pump current without any damage. Okay, the nice part about, after a while I didn't mind the presentation, Steon's, because I thought there's a few questions I can answer that were asked, and also introduce a few of the topics. And it's very much more practical. That, courtesy of ABB, is typical fluting damage of a ball bearing, a rolling element deep groove ball bearing. And there's the current. That should be smooth. And this is just showing the typical construction. There's your bearings, and Steon showed you where your currents flow. They either flow circulating in the frame, or they flow common mode where it's the same polarity to Earth. I'm just going to talk about the origins of shaft voltage, common mode and end-to-end. Thank you, Steon, for doing half of that for me. Homopolar DC shaft voltages. This is actually from the magnetic point of view. In other words, if you magnetize a shaft, and that's one of the often overlooked reasons for shaft currents, and it's also often the most destructive form of shaft currents. It's those sad stories you hear when they did maintenance on a powertrain and afterwards the gears were melted and whatever. Why are shaft voltages and currents important? Well, obviously because they damage machines. Well, the voltages don't, but the currents that flow do. DOL induced, so sinusoidal. VSD, I can brush through that fairly quickly because Stian's done most of it. What causes shaft currents to flow? So just to take a step back and look at it to give an understanding, because sometimes the current flow is quite complex. I mean, it's complex even in yours just showing just the motor. And when you get to the cables and everything else, it actually can be a lot more complex. Then I'll look at the difference between rolling element bearings and sleeve bearings. This was quite an interesting one because I had the same question that someone here had earlier, and I went and looked this up, and I'll give you my sort of interpretation of what I found, and I don't pretend to have found even close to what's available, but you can see what you feel about my explanation. Then the importance of the driven equipment, cables, auxiliaries, etc., i.e. the complete system. Types of earth brushes, insulated bearings, the options and types, and then some examples of real shaft voltages. Ironically, both related to SAIEE. I was lucky enough to take some measurements on a VSD-driven 850 kilowatt machine, and we actually took shaft voltage and current measurements. And it's with and without brushes. It's using the local version of, no offense, but of the Aegis microfiber things. I'm not going to mention names because I think it's out of, I don't want to go down the route of a previous magnetic coupling presentation. And then magnetism and degaussing. And this is very important because even when we had a previous presentation on shaft voltages and currents, this was completely overlooked. And it's a common cause of serious shaft currents. And then best practices. The few that I actually forgot about common mode chokes. A common mode choke is actually quite nice. It's just a core that you put in a zero sequence around your three cores. Yeah. Okay. The main cause of shaft voltages. Now this is 50 hertz. It applies to high frequency as well. And Stian introduced it, but you treat your shaft as a single turn conductor. And if you have flux linking that turn, you'll have a voltage across it. So if you look at a 4-pole machine, that it's got that field that rotates around it. And the reason why asymmetry is so important is if the machine is perfectly symmetrical and your voltage supply is perfect, those fields will just rotate and no one part of the field will penetrate the shaft anymore. So you will have no net flux linkage across the center line of the shaft. If you do, you have a shaft voltage. So the causes of that are ducts that are not, each time the flux tries to pass those, it'll change. And then Stian's example was of a keyway in a shaft. So, and no machine is built perfectly, so they all have a shaft voltage. Let's go back. So there's your magnetic asymmetry. Then you can also have I call it electromagnetic asymmetry, and it's related to your power supply. So if you have an unbalanced power supply, your U1 plus U2 plus U3 does not equal 0. So what you'll have both a common mode voltage on the shaft, and you will also have flux linking the shaft. So you have a number of problems, and of course supply faults. Often if you have a line-to-line fault on a machine and it fails, you'll find that the earth brush has gouged a arcing path into the shaft. VSDs, Stian's mentioned this. Then also unwanted magnetization of machine components. I say unwanted because of course you've got lots of magnetic fields in a machine. Your unwanted locations are typically on a bearing housing, your shaft near the journals, areas like that. And then also electrostatically induced shaft voltages. Wet steam in turbines and compressors, and interestingly enough, the VSD application that I measured was a fan, and we measured tremendous shaft voltage. way more than due to from the VSD, just due when the driven load was connected. That's an example of your unbalance if you at a certain stage in the machine, and well, that's VSDs for obvious reasons. Okay, common mode and differential. You'll now understand the differential. So you have a voltage induced across the shaft. The common mode, the way it's caused is if you look at a motor stator is hardly ever grounded. So the voltage that it adopts is equal to your equivalent star point voltage because of the capacitive coupling between the windings. So if you go and measure on a perfectly balanced supply and whatever, measure between the frame and neutral, you'll get 0 volts. However, if your U1 plus U2 plus U3 does not equal to 0, then your capacitive coupling between the winding and the stator core caused the stator core to adopt the neutral point voltage, so i.e. the common mode voltage. And that's how you get it both in the VSD form and in direct online or power frequency form. The reason it's not so much of an issue in power frequency is because your capacitive impedance between your stator and rotor is much lower for 50 hertz than it is for the 100 kilohertz and above that Stian's presentation was about. Okay, so magnetic asymmetry causes end-to-end shaft voltages, unbalanced power supply. That would cause both, because you'd have your effective stator frame voltage changing, and you'd have an end-to-end voltage. Magnetized machine components mainly cause circulating currents. I'll explain that just now, and end-to-end voltages. Electrostatically induced shaft voltages are effectively common mode because they normally originate from the driven load or prime mover. So your driven load and your voltage couples back and drives through the motor. Now, why would one bother about earth brushes anyway on a motor? Why not just insulate both bearings and just let the shaft float? Because, sorry? Well, you'd have an electrostatic voltage generated on that as well. So you need to do some form of earthing. So the reason why they often earth, for instance, on an EX application, you'll have to ensure that you don't allow a floating rotor system just to go up into sort of electrostatic voltages and then have continuous breakdown. Even though that continuous breakdown might not destroy anything over time, it could be a risk in terms of explosive environments and things like that. And then, of course, you'll see that there's because of the different types of shaft voltages and currents and everything, there's different methods to treat them. I've mentioned this. The one important thing is over here. No machine is perfect, so all machines have some end-to-end shaft voltage. And the two machines that we measured for Sassel, the one had a shaft voltage of 1.2 volts RMS, and the other one, supposedly identical, had 200 millivolts or 160 millivolts. And that can give you the difference between the two. Just two machines, identical design really, but just differently manufactured. And your magnetic asymmetries can be designed in or manufactured. So, like I showed you a few where that's a design that will have an effect on shaft voltages. And then, okay, this is why most motors above a certain size have the non-drive end bearing insulated. Why? To break that current path. So your current will want to circulate through the frame of the motor from one end to one end to the other via the bearings. So you insulate one bearing and you break that current path. Why is it the non-drive end? Because because typically you've got control over the non-drive end, nothing's connected to it. You never know what's, well, you should know, but typically the drive end will be earthed via the driven equipment. It could have it's got all its own issues. So you insulate the side that you have control over. Okay, no other examples here. You've got 3. Now, you know, it's better to have an even number of axial ducts or imperfections, but there's 3. And one of the common things is your spider construction. So imagine, I did show you in the previous slide, there was an FEA plot of something like that. So that will also, as your flux path crosses through here, it will have a different reluctance, and you'll have a shaft voltage induced. Okay, I think I've dealt with all of these. Your unbalanced power supply, so you've got 0 phase sequence and negative phase sequence components. The negative phase sequence just cause a field to rotate in the other direction, so it should have a pretty similar effect to positive phase sequence, just that the frequency will be higher. And then, okay, this is pretty much Stian's presentation, that your instantaneous switching in your power devices in a VSD make it unavoidable, really, that you have a common mode voltage, and that your stator core will be forced to adopt that voltage. And if you've got common mode currents flowing, they flow capacitively via the air gap, and if they're high frequencies and it's a small air gap, you will have reasonable current levels. Okay. Same thing here. VSD installations, I'm not going to go into, this is a topic on its own, but they can be very problematic. Everything's important. The load, the coupling, the supply cabling, shielding, earthing, and earthing brushes. So the whole lot is, and for example, a good idea is to fit an insulated coupling. And on more than one occasion, we've had a case where a drivetrain has been maintained, and then the coupling insulation has been left out or whatever for some reason, and the machines had bearing current issues after that. Yeah, I didn't understand this until your presentation, where you can have common mode and end-to-end shaft currents on VSDs. Until then, I had always thought you only have common mode. And this is a thing from it's from Aegis, where they show where you consider both, and then that there's the difference between fluting, frosting, and pitting on a microscopic basis. Okay, magnetism induced shaft voltage. What typically happens is a drivetrain's maintained, somebody welds on it, and they don't put the earth very close to where the welding's taking place. So you get quite large currents circulating, and you could have, let's say, you have your shaft underneath in the journal area having a north and a south component. So then you have a north and south spinning with megawatts behind it, and all the energy that it becomes like a synchronous generator generating into the bearing, and the power is all supplied from the rotor. So it's mechanical power from the rotor. So it can be like a gigantic welding machine. And that's how you see this destruction that often occurs. You can also magnetize the bearing housing, and that's where you get a homopolar shaft voltage. And that's DC. That's, another reason, faults. If you have had a fault on a machine, and you've had massive currents flowing through it. I had a case where another repair company that does DC machines did a machine, and they connected all the DC field poles in the same direction instead of north-south, north-south. And afterwards they found that the shaft was magnetized. And the reason the shaft was magnetized is you had all these poles pushing flux into the armature, and it had to come out somewhere. And it came out via the bearings and magnetized the shaft, and the rotor had to be taken out and demagnetized. And here you can have if you have a magnetism there, for example, you can have current circulating in a very local portion of the bearing. And you'll see that quite often in some bearings. You'll wonder how the current path could exist, but it's actually just a local path. So much so that you could call it an eddy current, not a full defined current path type current. And again, there it's one of the most destructive causes of shaft current. Other causes I've already put electrostatic turbines, wet steam fans. And then I said, yeah, standard high-speed motor drives. That's what I was saying about that. You can have a standard drive, and if you don't have some form of shaft grounding, you can have a significant amount of electrostatic voltage build-up on the shaft. So you need to do something. And this is a typical installation where why only put one set of brushes here in one place? Yeah, Peter's answered with his head. Often, and someone mentioned this earlier from Arnott, is you have, if you've got a voltage across from here end to end, if you put brushes there and there, what's going to happen? You're going to give the current a path to flow, and if it's a high current, your brushes will last a couple of weeks. So ideally, you want to find one point to earth, and then you can see here they actually monitor the voltage. And this is from MPS, Magnetic Products and Services. They came up with the whole concept of using shaft voltage and current as a monitoring tool, because your shaft voltage generally is related to axial flux. And you can use, by monitoring your shaft voltage and looking at the different characteristics, you can monitor your plants. You can go look that up on your own. This is where the origin of homopolar DC shaft voltages. So if your bearing is magnetized here, and you've got a north there and a south there, for example, and your shaft spins, you get a Hall effect occurring, and you get a voltage, a DC voltage across the shaft. It won't be AC. So that, any of you have ever come across a DC shaft voltage, that's what it's caused by, as well as the phenomena that Stian mentioned. Well, this is self-explanatory. The causes of shaft currents are the fact that a shaft voltage exists, and you need a current path, and you need that current path to be closed. So ideally, to prevent the shaft currents, you've got to remove the shaft voltage. It's almost impossible. Or you break the current path, or you divert the current. So you put insulated bearings in, insulated couplings, insulated bearing pedestals, if you can't, and then you put earth brushes in and to divert. So even if you've got insulated bearings, you put an earth brush in to divert what current might go through the bearing, not away from it. Because even if you don't have breakdown of your oil film in a bearing, you can still have degradation of the grease or the oil due to currents. So especially on VSDs where the frequency is high. Okay, this is the thing. They're important because they damage machines. I mean, it's simple as that. This is your rolling element and your oil film and the thickness of it. And the question was asked with the difference between sleeve bearings and rolling bearings. Troy actually answered it. Your rolling bearings are more sensitive. You need a lower shaft voltage to cause damage. Sleeve bearings are much more, can tolerate more. And even the difference between a cylindrical roller bearing versus a ball, because you've got a narrow, smaller contact point. So your oil film will be thinner. I've already discussed this. Also, just there, power supply harmonics, another cause of shaft voltages. Otherwise, the rest is pretty much a repeat of everything before. Rolling element bearings and sleeve bearings. This is actually a model of the interface between the bearing, the rotating part of the bearing and the stationary part. Already brought up in Stian's presentation. That's a sleeve bearing. It's a rolling bearing. There's your different types of elements. So you can have balls, smaller point contact, cylindrical rollers. That's a spherical roller bearing. And this is what I found, is that for rolling element bearings, your oil film thickness varies from about that 1,000th of a millimeter to 200ths. I can give you the reference of that. It's Prochard. And so this is considerably thinner than your equivalent sleeve bearing. So of course you'll have a lower breakdown voltage. Then I found another paper where the lowest breakdown that you get is around about 2 volts. Now of course it does depend on a lot of things. It depends on the size of the bearing, the lubricant, the speed it's running at, and whatever. So what someone mentioned earlier about 5 or 10 volts is about safe for a fairly decently sized rolling bearing machine. And then of course the types of rollers will change your oil film thickness as well. Then there's an increasing number of insulated rolling bearings options. I'll show that later, both InsoCoat and hybrid ceramic bearings. InsoCoat is SKF's trade name for a rolling bearing where you insulate either the outer ring or the inner ring with a ceramic coating, or both, I think. I don't know if they do both. There we go. That's there's your insulating coating. So it can be on the inner or outer ring, and then that's a normal uninsulated. So you see it's steel balls. Okay, there's typical damage from fluting. You've seen it already. And there's the different types again. This is what you can have. You can often have bearing currents due to other defects. And what's happened here? Well, you've got a heavy axial thrust or something that's caused this bearing to run for its load angle to be tremendously out, as well as shaft currents. And this here, you can see a certain amount of misalignment in the bearing, the way the line is not exactly symmetrical. Sleeve bearings, the oil film thickness, also, it really depends on whether you're talking about a bearing this big or a bearing this big, and you're talking about 100 RPM or 6,000 RPM. A 6,000 RPM machine of a decent size can have an oil film exceeding 0.5 millimeter. So the breakdown voltage that I found, the lowest one was about 20 volts. I see Troy's got some better things, and that's just a recollection. I couldn't find a similar thing recently on sleeve bearings, but generally they are much more resilient to shaft voltages. In terms of insulating them, you either insulate the shell around the bearing, or you insulate the pedestal, or you insulate the end shield. Those are the three main options. One thing about interesting thing about the ceramic coating is and I think Thijs Botha mentioned it about 6 months ago or so in a previous presentation, is that coating is so thin that its capacitance between the bearing and the housing is quite high, and so it often has limited effectiveness in high frequency VSD applications. Sorry?
There are papers on that.
Is it? Okay. Yeah, there's papers on it. If you, that's typical sleeve bearing damage. There's your oil film in a sleeve bearing. This is what I was saying, is often your bearing is insulated around here. Something quite important on big machines, you'll always find that both bearings are insulated, but you short out the drive end when the machine's running. I think there's a few of you here know the reason for that, but it's that if you want to check if the integrity of your non-drive end bearing insulation, how do you do it? You go and you measure between the shaft and the thing, and you go. If your drive end is uninsulated, you're going to get a short circuit. So the only way you can test is by opening that shorting link on the drive end bearing and checking both. So that's the only reason why it's done like that. Okay, the driven equipment, and I'll show you a oscilloscope trace later. if you have a common mode voltage and you've got both bearings insulated, okay, and but your load is earthed, you're going to have a lot of current going through your load. If you've got electrostatic voltage being generated by your load, if your load has had welding done on it, because you're far more likely to weld on your mechanical driven equipment than you are on your electrical rotating machine. So it can also pump current back into the system. And every earth point is important, both on your VSD or the one thing I'll show you later is this 850 kilowatt installation. It ran perfectly for 7 years. So that's an EX environment, VSD driven, 850 kilowatt machine. Ran perfectly for 7 years, came out for a standard overhaul, had the bearings replaced, went back into service. 3 months later it got taken out and it had not as severe fluting as I showed you earlier, but pretty much unacceptable fluting. And the reason we found was that the coupling guard was touching the part of the end shield that should have been insulated. So that I don't know if I've got a slide here, but let's say if you look at this is your end. Let's say you put insulation around that point. So your bearing, imagine your bearing sitting here was floating. The coupling guard was touching the section of bearing that should have been earthed. And that was enough to cause the bearing to fail. Well, fail. I mean, it would have failed after a few more months. It already reached about 12 millimeters per second vibration. And here, very important, I think someone even mentioned it earlier when we were chatting, is quite often you have this fantastic insulated bearing, insulated this, insulated that, and someone goes and puts a lube oil pipe onto the bearing and it's solid steel. Or they replace a bearing RTD that previously has an insulated tip and that touches the bearing. It's a very common, I see Fani nodding his head, so be careful with that. Okay, the insulated bearing types, those are the ceramic coating, and the next one is they are ceramic rolling elements. They're made of silicon nitride. I've heard the good thing about them is that they don't need lubrication because the friction is so low on these rolling elements that SKF say they don't need lubrication, so they run indefinitely. But I came across an end user in the Netherlands that is right on the tip edge or cutting edge of bearing speeds and things with their application. The application is rotary UPSs, and they used some of these bearings, and they found that the uniformity of the rolling element geometry is not fully up to scratch. So they ironically had problems with that. And of course, it's fully insulated because your inner ring is completely insulated from your outer ring, but you need to make sure that you have a non-conducting cage. Okay, onto the traces. This is the VSD installation. The voltage is blue and then the current is red. The scales are here in red. 3.2 volts will be 3.2 amps. So you can see you've got up to 1.6 amps of shaft current. And you can see the spikes go with the voltage, and then you can see there's a fairly sinusoidal. You're talking about a milliseconds, that's 2.5, and this goes with the drive switching frequency. Okay, that's on the drive end, with the drive end brush grounded. This is the drive end brush with the non-drive end brush grounded. So and you can't see it here yet, but I'll show you another trace where you can actually see the common mode voltages. So you get the voltage build up, and then you get the current, the current impulse for a while, then the voltage builds up again. Okay. This is the current. Just trying to remember. I didn't label that. Okay, that's the same one. This is the current on the drive end with the drive end brush grounded. In other words, what we're doing is we're seeing how much current the drive end brush is conducting. Okay, and that's 80 millivolts is 0.8 amps. So that's your N. Sorry. It's the same one. This is current, okay, with the drive end brush grounded and the non-drive end brush open, and that's the current on the drive end as well. And you can see the same thing where you get breakdown. See the influence there, and it's very similar to your breakdown pulses. Again, this is now 0.4 amps, and that's volts. Same one. Then this is the non-drive end with the non-drive end grounded and the drive end grounded. So you see different characteristics. Oh, by the way, I should tell you that this installation had two brushes, one on the drive end and one on the non-drive end. It was fitted initially with only a brush on the non-drive end. They figured out halfway through the project that they couldn't fit the brush on the drive end, so they put it on the non-drive end, which is actually the wrong place to have the brush. So we were lucky enough to be able to test currents with both brushes down. So with the one way, you're actually measuring the circulating current. When we measured this, for instance, this one, when you're measuring current with both brushes grounded, you're actually looking at the circulating current. So the way we managed to measure the circulating current was by comparing that current with the current of only one brush grounded. This is. Okay, that's the same. I just want to see if I can find the. Okay, here. This is the only voltage of the non-drive end with both brushes open circuited. Okay, so there's no earthing on this. Both brushes are open, but it's coupled to the load. So it's still got some form of grounding. It should have. And look at the voltage that you're measuring. 30 volts. Okay, and here, if you look carefully, you'll see the common mode. You see those raised sections. That's why I was saying I marked it how different, how classic your waveforms were, because this is a full installation. And this voltage here is clearly not related to the drive's common mode voltage, because on another set of measurements, when we measured without the fan coupled, it was much lower. So this is induced by the fan, so it's electrostatic, and that's why you get that high voltage. Remember, it's still earthed to some extent. It's not allowed to float completely. So now look at that voltage there. Then we put one brush down, and this is the microfiber brush. So when people ask how effective the brushes are, look at that. So you've got 30 volts there. Then with that's just zoomed in. I don't know why it's showing these. Maybe you can just see it better. You'll see what I mean about the common mode voltage there. Okay. Then this is with the brush, with the one brush earth, the non-drive end earth. Look at what the voltage has dropped to, 120 millivolts. So that's a microfiber brush, which is not generally considered to be as low resistance as let's say a bristle type brush or a silver graphite brush in good condition on a clean installation. So it's very effective, and it brings your voltage down by a massive amount, like sort of 50 times. So Okay, and then these were just measurements taken on another machine. This didn't have the load connected. So very similar. I'll show you the frequency components on another thing later. Also the same. Similar voltage levels. Also brushes fitted, but no load. We didn't have the opportunity to open circuit both these brushes because it was pouring with rain, and the link between the laptop and the digital scope failed at that point. Okay, then this is now direct online. So this is now a slow speed, quite a big machine. It's at about a 1.2 megawatt, 12 or 16 pole or something. I can't remember the details. In a test environment, and this is the shaft voltage measured from the shaft to earth directly. So what you can't see it here. I'll show you. There's a frequency spectrum later, but you see this component. That component happens to be 150 hertz. The supply was 50 hertz. These, the higher frequency components here are related to your slot harmonics, so your interaction between your stator and rotor slots. And then there's you can't see it, but a 50 hertz modulation. Okay, so this is effectively with the shaft allowed to float. Okay, then this is the shaft voltage measured directly end to end. So look at how you now get only your 150 hertz component, and the rest is, so it becomes pretty sinusoidal. Okay, and then the pure end to end is almost identical. So you see, you're still getting those higher frequency slot or slot harmonic interactions, but you've got a 150 hertz. Now, where does the 150 hertz come from? I asked myself the same question, and just to show you the spectrum, there's the 150 hertz. There's your 50 hertz, and these are your higher sort of 400s and your what's that, about 750. So that's typically your magnetic noise that you hear in a machine. So that's your slot harmonic interaction. And if you look at this is on a decibel scale. That's I think around about 0, and this is about 30 dBs down. So it's massive. It's predominantly 150 hertz. And the conclusion I came to is it's not related to a third harmonic. It's related to interaction between the number of whatever magnetic asymmetries that exist in the rotor, multiplying your 50 hertz by a certain amount. And this incidentally, the other motor shaft voltage is about 200 millivolts. Okay, brush types. There's your standard brush. Normally it's a graphite or metal graphite. The metal is normally copper, but silver was used quite extensively as an option. So it's silver graphite brush. There's a interesting one. I saw this. I haven't seen that in many industrial applications. And then another brush type here, your typical earthing brush where you put a carbon brush in. Then this is the well-known SAIEE turbo machinery brush. I think it's brass bristles that are gold plated. They cost a fortune, but they're still used in Eskom, am I right? On the big generators. Yeah. So sorry. Yeah, the braided now. Yeah, I'll mention that, or maybe you can. Incidentally, I had an interesting chat that the copper braid is now being used as a reliable and cost-effective and long-lasting option on the Eskom generators. But the problem with these brushes is if they take a significant current, they wear. And you can see they can wear very quickly, and they're very expensive. So that's other options. There's your microfiber ring. I couldn't find a picture of yours, but they're very, very similar. There's a SAIEE machine brush installed, so it doesn't only have to be the toothbrush arrangement. It can also be a sort of longitudinal or radial fit, and that's a silver graphite brush. I thought the relevant things that are is which earthing brushes are suitable for hazardous areas, and normal carbon, your carbon brush, whether it's silver graphite or whatever, is not. The ones that are the carbon microfiber in general. I think you still have to get them tested and whatever and approved. The SAIEE is as well. Incidentally, this was what was fitted on the SAIEE machine. It almost looks like a speed encoder, and it has a brush inside it. So that's how they get around the EX thing. The part that I found interesting was that that it had run for 7 years without any issues when you're actually shorting out your current path, because it was fitted on the non-drive end. So, but anyway, it functioned when we tested it and whatever, but that's one option. And then I mentioned the copper braid and strap. So this is becoming an important area of consideration, because there's more and more VSD applications, and more and more of them are in hazardous areas. So, magnetism and degaussing. Okay, it's simple. I've already brought up what the causes are. How do you determine it's there? You take a Gauss meter and you go and do a survey of, you measure all over the machine whether there's magnetism. If it's above 10 Gauss, then you normally consider it. And certainly if it's above 30 Gauss, then you need to consider demagnetizing. How do you demagnetize? You take ideally what you've got to do is you've got to put a coil around the component or the area of the shaft or whatever, and you've got to excite it to higher than the level that it's magnetized. So you have to put a substantial current through that coil, and then you reverse cycle it through the BH curve so that it continually cycles and goes to zero. You don't need to use a sinusoidal supply. These auto degauss units put a switched DC, so they go, let's say, 100 amps positive for like 2 seconds, then they switch 90 amps negative for 2 seconds, and they cycle down like that, and that demagnetizes the component. I've mentioned the causes. Take care after shutdowns and site work. This is what I was talking about, cycling it down. Identify the source. Wrap your degaussing cable around. It's not always straightforward. On big machines, it can be a very, very cumbersome issue to carry out. And of course, the bigger the component, the more current you need and the more number of turns. So years ago, I was asked to try and demagnetize a Duva rotor with that. And I told my boss, no, I don't think I could do it. My boss was Sherwin Jerry at the time. It was the Saturday of a public holiday weekend. And eventually he came and he said, no, he could do it. And he gave up after about 2 hours. And eventually, it was at Rotec. And Rotec eventually demagnetized it with a 1,000 amp supply and their own cable. And they just dropped it gradually. And then you just apply those currents. So you just decrease it with time. Often you have to disassemble the component, especially with bearings. So the correct procedure is to split up your into individual components and demagnetize them individually. So it can be complicated, but it can often be the only way that you'll resolve a serious shaft current issue. Okay, best practices. This is what I came up with. Insulate as many bearings as possible. Your insulation can be on your end shields or pedestals. Insulate couplings wherever possible. I understand that's quite expensive. Use shaft grounding brushes, but carefully. In other words, don't just use them all over the place. Put them in the right place and keep them to a minimum. Take care with auxiliaries and then earth components correctly. VSDs require extra care, cables, bearings, insulation, earthing brushes, filters, chokes, and then, very important, consider everything at the design stage. Don't try and resolve it after the fact when you've got problems on site. And then I'm open to, I said I did this as an introduction because you can see that some of these topics require a presentation on their own. And so there's obviously lots of other factors that one could consider and best practices that might be missing here. this is something I found on Aegis' site. Sorry about the really bad quality picture, but I couldn't find a better one. This is what they call an Aegis HF grounding strap. So for some reason, it's optimized to probably it might be made of Litz wire or something, continuously transposed wire, whatever, to have a lower impedance at high frequencies. And then what I found very interesting, this little bottle is colloidal silver. They actually recommend coating the shaft where your brush sits with colloidal silver. You can go and look at the website, it's Aegis. So that's why I'm saying I don't believe that it's a continually changing field, and the best practices will change along the way. Like, for example, your mercury brush or slip ring or whatever you. Specifications and guidelines, apart from the IEEE originated guideline of 300 millivolts, I don't believe there is any shaft voltage specification. They're also often very non-sinusoidal with high peak to RMS ratios. So you've got to be careful the way you measure it. You can have a shaft voltage that's got a sinusoidal component of 100 millivolts, and it has peaks of mass, like that one I showed earlier, the one with both brushes open. There's lots of commercial guidelines and proposals, but be careful with some. I think that you're going to get the commercial interests taking precedence. So look at things sensibly. The field is continually changing and learning, especially with VSDs, and matters get worse with VSDs in terms of specs. And often even quite experienced consultants, project houses, and that battle with this sort of stuff. It's not a lot of it's new, and there are genuinely no. I don't know if Gert, you can comment. You might have researched more than me. There's lots of papers, and lots of commercial stuff available and whatever, but not many guidelines. And then hazardous areas, they get even worse. And that's it.